our next speaker, and this is Stéphane Ménage at the University of Grenoble Alps, and he is a professor of chemistry at in Grenoble. And a little bit about him: he completed his PhD from University Paris-Sud in Orsay and postdoctoral training with Larry Kay at the University of Minnesota. He then returned to France and has served in various capacities and roles, responsibilities at the University of Grenoble until in 2011, when he became a laboratory director of the chemistry and biology lab, where he is currently. And Professor Ménage is also our chair of EuroBIC-15 to be held in Grenoble in 2022. His research interests include artificial enzymes and oxidase chemistry, and the title of his talk today is Deciphering the Mechanisms of Artificial Enzymes, a Rationale for the Unexpected Selectivity of an Artificial Ruthenium-Dependent Oxidase for Alkane Conversion. So please welcome Stéphane. Thank you.
Thank you, Siga. Is everybody hear me? It's fine?
Yes, I can hear you well.
I'll try to share the screen and there we go. So is everything fine? So you see the slide?
Looks good.
Okay, thank you. So thank you, Siga, again. So first, I would like to tell to everyone that I hope that all of you and your family have been protected from the COVID and that you're not too affected by this COVID situation. Second, I would like to thank Professor Suman and Eva for the EuroBIC organizations to put together this meeting and make the dream of EuroBIC alive. And I hope that in the future we will be able to meet in person somewhere, and in Grenoble, as you said already. This is very important for our community. And also, I have to say that I'm disappointed by not being in Iceland, but that will come. That I'm sure that I will visit your very nice Iceland. Okay, so finally, this lecture will be a little special for me because I will dedicate it to my colleague, Serge Crouzy, which is a great computational scientist who passed away last April. So I decided to take this opportunity for this present lecture to present some of our common recent achievements on the understanding of the mechanism of an artificial enzymes. This one would be a ruthenium-based oxidase for alkane conversion, thanks to experimental and theoretical approach. So in fact, this work corresponds to a very strong collaboration between three teams of our laboratory, the Laboratory of Chemistry and Biology of Metals, situated in the University Grenoble in Grenoble. And so I would like to point out the people who are very involved in the project. So first, Dr. Caroline Marché-Delapierre and Dr. Sarah Lopez, who were in charge of the chemistry part of the project. I would like also to point out the influence of Christine Cavazza and Chloé Lepret from the team BioCat, by making all the different experiments for the biologic part of the project. And as I've mentioned already, the work also has gained interest by doing calculations and that have been provided by Serge and one of his colleagues, Johan Moreau, from the MCT team. And in fact, I would like to say that this work actually has been initiated by a collaboration with Professor Nikolai Burzlav from the University of Friedrich Alexander for working on ruthenium chemistry. Okay, so as you all know, we are concerned by the development, or at least the advent of a sustainable world. Among all the strategies, there is still a need to develop new tools for a sustainable chemistry, following the principles of green chemistry. So in these principles, catalysis represents the cornerstone of the new ways or the good strategy to provide new chemistry. And when we think about this, we face a lot of challenge when we want to provide a sustainable oxidation catalysis, because as you know, we need to control the selectivity of the reactions in the term of site-directed one, chemo selectivity, or even enantiomer selectivity. And in fact, what we do usually is that when you do oxidation, the product of the reaction is more easily oxidizable than the substrates, or at least the reactants. Also, when oxidation catalysis is concerned, we need to think about the stability of these catalysts who are working on harsh conditions. And on top of that, you need to think about ways to provide a chemistry that will be following the green, the principles of this green chemistry. So as you know, the best strategy will be biocatalysis. And by doing this biocatalysis, you will be able to work in water using natural products, but this domain is not sufficient to provide all the chemical reactions that man-made can do. And for example, you need to expand the reaction scope to abiotic reaction, as Gerard already said before. So the answer to that is to help biocatalysis by putting some man-made work on that. And the answer to make this expansion is to make these artificial enzymes. So I will illustrate the structures, or at least the definitions of these artificial enzymes in a different way than Gerard has done already. And I will just concentrate on the oxidase artificial metal enzymes. So when you want to make this kind of artificial enzymes, the first way that you can, or the first strategy you can follow is to switch the metal, and this has been nicely done by Fujita in Japan when they removed the copper from cupene and add osmium, and they were able to make a very efficient catalytic system to do alkene transformation into diols with a very high turnover numbers. The second approach you can have is to do repurposing of natural metal enzymes. So this is mainly done by the groups and some groups, but especially the one of the Frances Arnold, sorry, where they use a CP450 variants to transform to go from an epoxidation to an anti-Markovnikov alkene oxidations, and they use directed evolutions to make the system very efficient. The third approach is to try to make a protein from scratch by using the knowledge of the self-assembly of polypeptides. And here is an example from 4 helix bundles that had been prepared and that self-assembled by itself by putting in the middle an iron active sites that is able then to oxidize amine into N oxides. And there is a fourth way, which consists to create or to reconstitute an enzyme de novo by introducing into a protein which is supposed not to have redox activity, okay? By putting inside this protein an inorganic complex that will play the role of the active sites. And this has been done, for example, recently with by putting into a steroid carrier protein using H2O2 as the oxidant, the transformation or the oxidations of lignin models. So this is this fourth approach that our lab has followed from the last 10 years at least, because we like the idea to prepare a modular catalyst. In fact, when you found a protein scaffold that is able to insert or to insert, sorry, an inorganic complex into its cavity, so you can remove it and put another one, and you can have then a different kind of activity. And what is also interesting is that you can think about separating the reactivity from the selectivity by saying that the inorganic complex will drive the reactivity while the selectivity will be controlled by the protein scaffold. So there is, even though Gerard said this is very complicated to do that and perhaps not worth it, we think that we can have a better idea and better optimizations of these hybrids by using modifications of the complex on the ligand, for example, to get a better activity, or to do mutations, site-directed mutagenesis on the proteins to optimize our systems. So the systems we have used or selected is NIKE, which is a protein which is able to bind nickel and has the properties of a nickel transport in E. coli. And here is the structure of the enzyme. And you see that there is a cavity in the middle. And in purple are the amino acid residues that are important to stabilize a substrate, or at least a ligand, and the nickel actually in the proteins. So in our case, we have selected this enzyme because it was able to bind iron DTA, and then we have made models of these systems and found that we can really stabilize systems into the cavity by using at least a ligand that will contain a carboxylate. And you see on this picture that you have, let's see how I can do that. I'll show you what's the pointer. Voilà, okay. So I will, the iron, this is an iron complex, sorry. So this iron complex, in fact, is stabilized into the cavity of the protein by the formation of a very strong salt bridge between an arginine, the arginine 137, and a carboxylate from the ligand. And the whole system is stabilized to, let's say, to a macro, with a KD around the macromolar level by P interaction between this tryptophan and the phenol present here. And this allows then to make a lot of combinations. And during the last 10 years, we have used this NIKE system as a platform for catalytic oxidations. We have, for example, introduced an iron complex containing aminopyridine ligands, and we were able to do oxidation of thioether with a good yield and good turnovers. We have also been able to introduce another complex into an iron complex into NIKE, and we were able to show that we can do hydroxylation of arines. And more recently, we have also switched from homogeneous to heterogeneous catalysis by using the NIKE crystals as a support to do reactions, and by introducing iron complexes into NIKE crystals, and we were able to make a very efficient oxidative cleavage of alkenes and even hydroxychlorenations. We can also, so I invite you to see this paper to see that really we can do heterogeneous catalysis using protein products. The thing is also that we can do hydroxychlorinations by using a ruthenium complex, and that will be the topic of my talk today. So you see, we have something which we have only one protein scaffold, and we can provide a lot of activities, which is what we want for another modular catalyst. So the aim of the studies today, in fact, was to show you, will be to show you that we can really separate to understand the mechanism of this artificial enzyme by separating the role of the catalyst from, or the inorganic catalyst or the inorganic complex from the protein scaffold. So to do so, we will compare the reactivity of our starting complex in aqueous medium alone or inside the protein scaffold of Nikkei. And we will try to go further and try to understand the reaction mechanism via an experimental theoretical approach. Okay, so what we have done first, we had the opportunity to get a nice complex with the ruthenium and a carboxylate from the group of Professor Burzlaff in the University of Erlangen that provide us the opportunity to use it, to insert it into Nikkei. When we use this complex, because it was shown also that in acetonitrile, it could be able to do epoxidations with a reasonable yield. And then when we transfer this system into water, there is no reactivity at all with alkenes. And this is the same behavior if you take the protein alone from Nikkei. We have used the hypervalent iodine of this kind, that we call it PIDA for the rest of the talk, because it was the preferred oxidant to do the epoxidations in organic solvents, but this ruthenium-1 complex. Now, when we inserted the complex into the protein, so when we mix the systems, what we get is something which was unexpected at the time because we were expected to get epoxide, but in fact we get oxochlorohydrins with a very good yield and based on the amount of chloride present in the medium. So this has been, we continue to understand the reactions. And in fact, we found that this hydrochlorination is very selective. And we found only one peak that has been determined by GC, and this is true for different substrates. And what you see here is that the traces in the absence of the protein scaffold is show that there is no reactivity at all. Okay, so we have a residue-specific selectivity for alpha-hydroxy beta chloride. We have looked for a substrate scope for these systems, and we then found out that this hybrid system is very reactive, not only for aromatic alkenes, but also for non-aromatic or aliphatic, cyclic ones. And we found also that in the case of the methyl cinnamate, we did not have any reactivity. So we will keep that for later. But again, for all these substrates, we get the same kind of product, which is this alpha-hydroxy beta chloride. Okay, so we have found also that the reaction is stereospecific, and we have a diastereomeric excess that depends of the isomer of the beta-methylstyrene. With the trans-beta-methylstyrene, we get a diastereomeric excess of 6.5 to 1. And this is inverted when we start with the cis system, but with a lower value in the case of the cis. This has been determined by the GC using a chiral column, so we can see all the enantiomers. Okay. Then, since we have a system that works, we wanted to understand why the complex and the protein, or what were the difference between the complex in the aqueous medium and into the protein could affect the reactivity. So we look for structural studies. So on the left, you have the structure of the ruthenium called ruthenium-1. And you see that you have the carboxylide, the 2CO, and they are aligned to the ruthenium, so with a ruthenium CO of 180 degrees, and which is expected for ruthenium-2 with distances expected from a ruthenium-2 low spin. When we were able, and we were lucky, to get the X-ray structure on the system into the protein. And we see, in fact, that we have two types of structures. The first one is close to ruthenium-1, but what we see is that the main difference actually is the bent ruthenium-CO angle around 118 degrees that was not expected, and we interpreted that by the fact that it was in fact a mix of the different CO orientations, meaning that this CO was ready to be removed. And this has been really confirmed by the fact that in some cases, and I will call now the new structure is called ruthenium-2. In this case, the CO has been removed and there is replaced by the water molecules. Then we try to see what happens in solutions, and we compare now the FTIR traces for the complex alone or into the protein scaffold or into the hybrid. And what you see is that the ruthenium-1 provides you two vibrations which correspond to the 2CO as expected. And when you look the traces for the hybrid, you find three different traces. Two are close to the ruthenium-1 and one is new. And we challenge then this for the interpretations. We challenge the calculations to provide us the new CO energy vibrations, and we found out that in fact, despite the fact that they were just not displaced by 50 or 70 web numbers from the experimental version, we see that the difference in energy were the same for ruthenium-1. So, and we do the same for ruthenium for the last systems, and in fact, we calculate the vibrations of the CO from the RA2 structures, and we find that it was in the same area. So that means that the hybrid systems provide you a mixture of ruthenium-1 and ruthenium-2 when it is inside the protein. Okay, now if we compare to what happened to the ruthenium alone, we use EasyMS to look for the integrity of the complex, and we found that it's really kept the same. It's kept the same at least at first, and as a function of time, we see the formations of a new fragment that correspond, in fact, to the release of the chloride and the replacement by the water molecules from the solvent. So as a function of time, you have the loss of this chloride. And this has been also proven by a molar conductivity experiment where we see a good agreement with a one-to-one electrolyte. So we see that when the complex alone is in solution, it loses the chloride, while when it is present in the proteins, it loses the CO. Okay, so we continue to try to expand the scope, the substrate scope of our systems. And in fact, we found something which was quite striking at first, because we, when we take an aromatic alkanes that was very more enriched by the presence of these methoxy dispositions, we did not get the alpha hydroxo beta chloride rings, but instead we take an epoxide. And then we have a systems which is very efficient, because it can go up to 175 turnovers with a 35% yield. And also it's really accelerated the reactions, because now you have 18 turnover frequencies per minute. And if it's very faster than the complex alone in organic solvent. Okay. So we decide then to track, or to try to decipher the mechanism to understand what was the difference between all these difference in the reactivity between these two substrates. So for the following on of the talk, I will probably use sometimes a BMS for trans-beta-methylstyrene, and methoxy and MOS for methoxystyrene. So be aware of that. And what we see is that for whatever the conditions we used, we found the same behavior despite the, or at least despite the difference in the product. So that means we believe that the reaction goes through the same mechanistic pathway. So to understand mechanism, we change the nature of the oxidant in order to see, to have a better idea what could be the oxidizing systems. And then the first row is the PIDA, which is the diacetoiodazobenzene that we use. And we have seen also that this PIDA can be transformed by an excess of chloride in solutions into this dichloroiodobenzene, which is a very good chloronium adduct. And in fact, when we use it, we get, as expected, hydroxychlorinations, but even in the case of MOS. So this is not the real active species. We have also found in literature that these PIDA can also be transformed by disproportionations using ruthenium chloride as a metal to form this diiodobenzene, which is the very strong oxidant. And you see that in our case, is not catalyzed, it doesn't participate to the catalysis at all. On the other hand, the system that provides the same selectivity is iodobenzene. Okay, meaning that we are forming the same oxidizing species if we start with PIDA or FeO. And also we thought that perhaps since we are making chloride adduct, perhaps we could go through a pathway where we can form sodium hypochlorite, or at least hypochlorite anions. And when we use sodium hypochlorite, we found that the reactivity is not the same, because all the systems provide you the hydroxychlorohydrin product. So the fact that only the FeO, PIDA and FeO provide you the same behavior means for us that would suggest that we have an oxygen transfer more likely than a chloro transfer. So this was suggestion. So we continue. If we look through all the different pathways that can happen, in fact we have two main systems. The first one will be, or the two main reactions. One will be a metal Lewis acids or a redox processes. So first, we propose that there is no really amino acid based Lewis acid catalysis, because when we use the protein alone is not working. The fact that if we use the ruthenium alone, ruthenium-1 or ruthenium trichlororuthenium is not working at all. Also, that means they are not playing a role of Lewis acid. And if we look now into the protein, we found that if the ligand is not present, there is no reactivity. So the ligand is important. So this is not adventitious ruthenium or aspecific ones. And also to give more hint about possible metal Lewis acid catalysis, we replace ruthenium magnesium into the cavity, and we didn't find any reactivity. And this is true again with both substrate, meaning that, or confirming at least to ourselves, that we are following the same catalytic process for both substrates. Okay, now the fact that we have a diastero isomeric effect, diastero isomeric ratio, sorry, showed that, suggests that we have a stepwise reactions, meaning that we go through an intermediate. And the first two that you can think about is the fact that you can go through an intermediate that will be an epoxide, and this epoxide will be opened by the presence of the chloride. In the case of the trans-methylstyrene, but it does not happen because when we do that under catalytic conditions, we get diols. Now, if you do this with 4-methylstyrene, you can expect the reverse reactions will be based activations to eliminate the chloride and to make the epoxide on this case, but it's not working when we when we put this alpha hydroxy chloro from the methoxy substituent of the alkene, it's not working at all, and you don't get the epoxide. So this is not what happened. Okay, so we would like to go further and say, well, can we trap a metal-based intermediate? And what we did is that we followed the reaction by UV visible and look for the kinetics. And in fact, what we see is that when we add PIDA to the protein and containing the ruthenium, we see the appearance of charge transfer band around 560 nanometers. And when it is maximized, we add MOS or BMS as substrate, and directly this charge transfer band disappears as a function of time, as you can see here and here. Okay, meaning that we have trapped something which is reactive with this substrate and is involved in the catalytic process. We find out also that we can have the same phenomenon using iodosobenzene, saying that again, these two oxidants are related and provide the same mechanistic pathway. Note that if you take the complex in the absence of the protein scaffold, you have no formations, or at least we cannot trap any intermediates in this case. So that means, again, the fact that you put your complex into the proteins orients the reactivity, and probably because you remove one of the CO and not the chloride. Okay, the question is, what is the nature of this oxidant? So we challenge the nature of this intermediate by calculations, and then we do computational studies on ruthenium oxo, which has this structure, and that will be surrounded by the most closest amino acid residues. And by doing that, we reconstruct the electronic spectra, and we found out that we have good correlations between the energy found in our case and in the case of this calculated one with a maximum around 600, and this transition correspond to transition from the electron from the chloride that go through a non-bonding orbital on the oxygen. Okay, so here is where we are so far. This is all the possibilities that are left. The idea about Lewis acid activations seems not really, it can be excluded. So that means that the ruthenium-2 that activate the double bond is probably not occurring. But the complex that will react with the hypervalent iodine can make first a ruthenium-2 oxo or oxygen, iode, and phenyl that will be the same intermediate that you can form with iodosobenzene. These systems can be reacting directly to make the product, or you can consider that you break the OI bond and you form a ruthenium oxo, as we suspect from the kinetics or UV kinetics experiments. And also there is two ways now. So either this system is able to make directly the product, or you can activate chloride to make this ruthenium OCLs that will be this ruthenium hypochloride adduct. And this will be a redox processes. So to find or to understand what will be the mechanism of the reaction, but also to determine the active species for the icon transformation, to explain the selectivity of the reaction depending on the both substrate, and then emphasize the role of the protein, we decide to make computational studies, by using DFT methods with dysfunctionals and this kind of corrections. To determine the energy steps and the energy diagrams, we do a PET scan for each step. Okay, so first, we have to determine the electronics and the structure of the starting systems, or ruthenium-2. So this has been done with the ruthenium-1 and ruthenium-2. And we have found that the more stable state of the ruthenium-2 is low spin, while the high spin go at least 25 to 50 cars per mole above. Okay, we also compare the structures observed or calculated to the one observed in the protein, and we found that the best is the ones that have been done for the singlet states of the ruthenium. Okay, and especially based on the distances between the ruthenium and this carboxylate. Okay, so now we have optimized the geometry of the starting ruthenium, and we first think about the first steps of the reaction, which consist of the activations of PIDA, this hypervalent iodine. So we found that the first step of to start, in fact, is the ruthenium with this PIDA, where you have hydrogen bonds between the ruthenium and the water molecules. If we do the same with ruthenium-1, we've never been able to get any transition states and to find any pathway. So that means ruthenium-2, as I said, the ruthenium-2 with the aqua adduct is the most reactive one, and we will concentrate on this one. So this react with the ruthenium to lose one of the carboxylate, and to make in the acyclic triplet states one intermediate that directly goes to the formations of the high valent ruthenium-4 oxo. Now, if you go to the singlet states, you have two steps, and that provide you this new intermediate that will be further from this one, where you release the second carboxylate and you make the intermediate ruthenium-EO, and this is this one that is not stable, and it very easily is transformed to the ruthenium oxo species. So we believe from that this cannot be the intermediate that react directly with the double bond to make the hydroxy chlorohydrin. Okay, Now we have to exclude other possibilities. First, we did the calculations to see if we can do the reactivity with the ruthenium oxochloride, with the hypochlorine adduct, and you found that in this case the chloride has a positive value pretty small, which is not really accurate to metachloronium. So, but anyway, we try to do by PET scan see if we can activate a double bond, and we never been able to see any transition states or whatever. So on this basis, we exclude this ruthenium-2 OCl as the oxidizing species. So we finish then with this ruthenium-4 oxo species. And we see that in this case, you will have an oxygen which is not very electrophilic because it has a negative value around 0.25. But anyway, we look now for the second reaction steps, which consist to deactivations of the double bond to make the products. We found that when we start with DMOS, so the 4-methoxystyrene, we have from the singlet states only one transient state, which is a direct active oxygen insertion into the double bond to make the epoxide, which is the most stable species at the end. Now, if you start with the triplet states, what you have, which is again the most stable one, so ruthenium has to be S equal 1. What you see is that you have two possibilities, an attack on the C alpha carbon or on the C beta carbon. And you see that the attack on the C beta carbon is preferred by at least 10 kilocars. And you see that you form a ruthenium 3 with a radical on the C beta positions, while on the other end, in the other case, sorry, you form a radical on the C beta positions. And this system can be transformed to the product that provide, in every case, the epoxide. Note that these values are pretty high, and so we believe that during the process, because we know that this is ruthenium-2, this final ruthenium is ruthenium-2, and it's S equals 0 state, we have a spin flip that has been proposed from several times by Professor Sejanchek, and in the case of ruthenium chemistry by Professor Wenwu Nam. So we believe that during the process there is possibility to have a spin flip that will be hypothesized to be here. Okay, now in the case of BMS, what you see is that we have the oxidations to same processes. So with the singlet state, we found again only one transition state, okay, that provide the right product, which is the alpha hydroxychlorohydrin. Now, when you do it with the triplet state that we believe is occurring, we have in both cases on the different attack on the carbons, we have the same intermediate, which is the ruthenium-3 with a radical on the alpha positions. And we found that there is a huge transitions that provide you, in one case, the epoxide, in the other case, a precursor to make the alpha hydroxychlorohydrin. So that means with the BMS, you have possibilities of both. And we believe that it can be expelled on the basis of the product obtained. Nevertheless, now we have an idea how we can explain reactivity only concerning the complex. But now, if we have to look for the role of the protein scaffold. So what we have done, and as I said before, we in fact surrounded the ruthenium oxo systems by 4 amino acid residues that have been blocked on C alpha and C beta positions, and let it go and see if we can find the same pathways. And in fact, what we see first is that the energy are quite similar, okay? But what we see is that there is some orientation that have been found with the complex, the energy diagrams for the complex only, that are not possible anymore because there is some orientations that will be excluded because it clashes with the some amino acids, and in particular this TRP398. So this is true for the state I, but this is for the BMS, but this is also true in the case for the 4-methoxy reactivity, and we found that E is okay. E is not okay when we start because you see that there is a problem of orientations and clash. Okay, so that means if we learn from that, that means the protein, in fact, select the orientations of the intermediates or the starting systems. And this is true also with in the case of the transistor set, as I said, because TS1 prime, this one cannot be retrieved where in the presence of the protein scaffold, while G prime is stabilized. Okay, so what does it mean? So that means that in fact, we can say that the role of the protein, in fact, is to preclude all the systems that will be the most stable, because these systems are the best energies, but in fact to make, and they are quite unreactive. So to make them reactive, you have to lower this barrier, and this is done by the protein scaffold. Okay, so to enter the final slides, will be our interpretations. And what I would like to say is that when we use the MOS as substrate, what we see is that we directly goes to the epoxide via an attack on the C beta, and you have then the close of the oxygen to the C alpha carbon to make the epoxide, because this chloride cannot be transferred. On the other hand, if you go to the BMS, what you see is something a little different, because in this case we can consider both attack on C alpha and C beta. We get the same intermediates, but they will have different orientations, one precluding the transfer of the chloride to make the hydroxychlorohydrin, which is the observed products. So in fact, this means that we are going through the pathway where we use the C alpha attack first. And we believe that the height of this energy barrier for going through the epoxide, in fact, is not formed because it's too high, and it goes back to the start, and we go to the attack on the C alpha. So you see that the proteins help then to manipulate or to choose the right, helps to stabilize the right compounds. Okay, so I'm done. So I would like to say that we have made very good artificial enzymes to do hydroxychlorogenations. We have also made systems which is very efficient and selective for anabiotic reactions. We have shown you, I hope I was clear enough to show you that we can make a distinction between thermodynamic and steric effects by and looking what the inorganic complex does and what does the proteins. And we have shown you on this example that we can promote the starting oxidizing species, as we see by the exchange of these CO ligands, and we can control, and the protein can control the substrate orientations. So this is kind of obvious when you think about natural enzyme, but it's better if you can show it in artificial enzymes. Okay, so I would like then to thank the people who have done the work, Serge, for what he has done for all over the years, and especially on this project. Professor Nikolai Burzlav for providing the ruthenium chemistry, the ruthenium complex, and to have very nice discussions during the writing of the papers. And also I would like to thank all the people who have done the work, Caroline for the chemistry part of the work, Christine Cavazza for the work done on the biologic part of the project, and especially thanks to Sarah Lopez, who for what you have heard today is directly our own PhD work. I will thank the university, the CNRS, the CA for the financial and for support, and for financial support, the ANR, Arcan, and the MBG, and I thank you for your attention.